Oh, I don't want that. I want to record again. I guess I am recording. Okay. Let's start. This is lesson two. We don't know what we don't know. And in lesson one, we kind of talked about some of the problems with how we think about anything, and the fact that there are always assumptions in everything that we do, and we can't even start talking about anything without first making some assumptions. Today, I want to dig into that a little more, and I want to dig into actually generating what I'd call a natural philosophy, a way of interpreting ideas for science. And so, as you can see in our little handout here, Wikipedia calls natural philosophy, they say that it was the philosophical study of nature and the physical universe that was dominant before the development of modern science. It's considered to be a precursor of natural sciences such as physics. So, in other words, natural philosophy is old stuff, and we don't really, it's kind of like flat Earth. We don't need natural philosophy anymore. It's just part of our history. That's Wikipedia's idea of what a natural philosophy is. And that is not what I mean when I'm talking about a natural philosophy. It's not something old, it's something that's absolutely necessary. So if you read on, it says natural philosophy can also be defined as the fundamental set of assumptions, definitions, and conventions. We'll talk about what each of those things are that form the basis for how we look at physics and other branches of science. And this is a kind of natural philosophy that's not optional. Even if you don't think you have one, guess what? You have one. And so the question is, can we, rather than just get one by default, rather than just get a natural philosophy by having it sort of inbred into us or having it cooked into us through the public schools, let's be intentional about this and actually develop a natural philosophy and think about what it is that we're developing. And so, what I want to do today is give us a method, give us a means, a mechanism by which to develop a natural philosophy. And it could be that you wind up with a different one than I have, and that's okay. So, I'm going to give you mine, but I'll give it to you as an example, not as a set of truth that you have to accept. Because the whole point here is that if you and I think identically about everything, then one of us is unnecessary. And so it's okay for us to come up with a different set of assumptions, definitions, and conventions, and that's going to give us a different natural philosophy, a different way of looking at it. So anyway, what we're going to do is just talk a little bit about that, about how we go about doing that intentional business of creating a natural philosophy. But before we can even do that, I want to talk about what we can't do, what science is not able to do, and what it thinks it can do, or at least conventional science thinks it's able to do, but really isn't able to do. That doesn't mean science is worthless. It just means that it has limits. So let's talk about that right now. First thing is what I call the limits of proof. And I have a slide here that says, what is a scientist's favorite game? And I don't know, anybody, what do you think is a scientist's favorite game? Yeah, you said, yeah, chess or whatever. Some other, we can get some feedback from the audience, but basically, I think the scientist's favorite game is proving everybody else wrong. So in the Natural Philosophy Alliance, we have people who like to prove that Einstein was wrong, or that Maxwell was wrong, or that Newton was wrong, or that this guy over here, for sure, he was wrong. And of course, you are wrong, and I am right. That's what scientists love to do more than anything else, is prove everybody else is wrong. And I can't tell you how often I hear the word prove. And this proves this, and this proves that, and I've proven such and such. Um, and I always cringe whenever I hear the word prove. I've gotten to the point where if anybody says the word prove, I get a physical reaction that I tighten up and I think, oh, not again, not another one of these. Because if they really truly had proven something, then of course everybody would agree with it, and there would be no more argument. I mean, that's what a proof is supposed to be.
Greg, I'm going to interject.
Sure.
I think that's a wrong conclusion that if something had been proved, that everybody would agree with it. There's lots of things that have been proven that people disagree with, and that has less to do with reality than with their perception and their brains not working right.
Sure.
So I disagree with that statement.
Sure, I understand. And again, now I think what we need to do probably is spend a little time talking about what the word prove really means. So, again, a person can so-called prove something, and what they're doing is they're taking a set of assumptions and conventions and definitions, and then they're using that as a basis. Given these ideas, then I can show logically that some other thing follows, and that would be called a proof. My point here is that the proof itself has nothing to do with the assumptions, definitions, and conventions that you begin with. It's only the process of taking those things and then logically drawing some conclusions from that. That can be called a proof. Okay, so in other words, proof lies strictly in the realm of logic and mathematics. It is not something that you can actually show directly from experiment, because before we have to process, we have to take the experimental data, then we have to interpret what that means. We have to again say what we think that is going on. We have to make some simplifications, and that should probably be added to our list: assumptions, definitions, conventions, and simplifications, or modeling. Okay, which is what when we take a physical process which is really complex and try to make it simpler, we are doing just that. And so that's what proof is taking all of that data which is pre-proof, before proof, and then the steps of proof are relatively easy, and as long as they follow those logical steps, nobody's going to argue with them. But what they're going to argue with is the unstated assumptions, definitions, and conventions. And that's where all the argument is, and that's what's never acknowledged, is that you've got a different set of assumptions and definitions than I have, and we're never going to come to agreement on that. And so I can sit here and prove things all day long, and it's not going to make any difference because you're not agreeing with the way I'm interpreting the data. Okay, and I'm going to give you a real simple example of what I mean. I'm going to ask you to think about proving 1 plus 1 equals 2. Well, in order to do that, we first have to have the concept of what is 1. What does the number 1 mean? Okay, and that may sound like a trivial thing, but when you're at some point in your life, when you were a kid, you had to understand the concept of oneness and the concept of two. It wasn't trivial. It's a very, I mean, we all are familiar with the idea that the number 1 and 1, raisin is different. The raisin is different than the number 1, but the number 1 we can also have 2 hands, but the 2 is not the hands. It's a different concept. So we have to get that concept in our mind. Then we have to get the concept of addition. What does that actually mean to add things together and get something else? Then we have to have the concept of equality. Okay, when we say that something on the right hand side and this something is equals something on the left hand side. Then we have to have the concept of symbols to match each of these. A symbol for addition. Those are conventions. Okay, so we accept that the little plus sign here means addition. That's a convention, and it isn't as though that's a cast in stone thing. We could have used some other sign to mean addition, and then that would be a new convention. As long as we all accept it and we all understand what it means, then we can accept it. But we have to have all of that background first. We have to define each of these, because then again, we're always talking about these things in terms of language. What does the number 1 mean? So again, we have all this background, assumptions, definitions, and conventions. That's 99% of the effort that's involved in proving that 1 plus 1 equals 2. Then the proof itself is relatively trivial. Okay, so I just want you to understand that all that background and all that hardware, that's the hard part, and that's what we spend very little time in physics. We kind of assume that we know all of this and that we all have that same background, that same hardware. Well, in the case of algebra, we probably do. But in the case of science, we may not. And that's where we break down. And that's why the realm of proof is difficult to even deal with. I can just take a little aside and talk about there's 2 schools of thought that have kind of been competing with each other for millennia. We have to go all the way back to Aristotle and Plato. And that would be what we call empiricism versus rationalism. And Aristotle was a proponent of empiricism, which is the idea that all we know is based on what we can get from our senses. We don't, and everything comes from that and doing experiments and things like that. The other side, the rationalist side, says no, the ideal world is the world of thought. This is Plato's way of thinking, and the actual manifestations of things, well, those are, those are lower things, and we were only concerned with the higher things of the thoughts themselves. And so what I want to say is that the idea, the realm of proof is in the realm of thought. It's in the realm of ideas. It's not something that we can tangibly do. There's nothing in the universe that proves or disproves anything. It's all really step by step. I mean, an animal that has no concept of the idea of proof. It's an idea. So we have to, first of all, understand that, yet the experimental data is all in the realm of stuff that we see in experiments. So there has to be this crossing from one side to the other involved in any proof. And that interpretation, that how do we take real world data and bring it into the realm of ideas so that we can generate proofs and mathematical equations, that's where we run into problems. And that's what we're going to be talking about a little bit today. A second limitation is the limitations of language. And language necessarily is finite. We have, no matter what language you're speaking, and I think English probably has more words than any other language, but it's still a finite number. And it's also imprecise, and it's also ambiguous. We have, certain words that mean more than one thing, and they might mean different things in different contexts, and we can use them in different ways, and that creates all kinds of great variety, which is great. And also the way we speak, our voice inflections tell us something about what we mean, communicate more than just the words themselves. So there's all kinds of ways that we communicate, but again, words alone are limited. And the best way that I know of to describe that limitation is a game called Vish, which maybe you've played it before. If you can take a dictionary and look up any word you want, and then give me a definition in terms of obviously words, and the fewer words the better. And then we take one of those words and I have to define that word, but I have to define it in terms of other words. And then eventually, then the third person then would take that definition and define, in fact, we could play this. I don't know if we have time to do that, but we could play this game, have somebody define a word and we could write it down, and then have somebody define the next word and write that down, and just keep going. Eventually, you're going to have to define it in terms of a word that's already on the list. It may not be the first word, but it'll be a word that's already there. And when you do, then everybody shouts out Vish, because we've got a vicious circle. And it's guaranteed that that will happen because there's only a finite number of words in the dictionary. So eventually you're going to have to come back. So that is one limitation of language. You cannot, the point being here is there has to be at least some subset of words, which maybe we could have some minimal subset in terms of which all the other words are defined. But there must be some set that you just have to leave undefined, or are defined in terms of something that's already defined. So if you want to, as a scientist, you want to have something where everything is defined, clearly. It's impossible because you cannot define everything in terms of something else. Something has to be left undefined. And there you go. That's the problem. That's where we have assumptions, definitions, and conclusions. That's what a natural philosophy is what is that basic subset? Okay, and that's what we're going to be talking about today. And one other point is, I've talked about the imprecision, but also there's emotional baggage that's tied with language. What I mean by that is, I may say a certain word, for example, like Bible. If I said the word Bible, then you would have an emotional reaction to that, and you might, even though we kind of both know what I mean by that, you're going to not want to hear what I have to say about that. Now in science, if you're not into science a lot, then this may not have a meaning for you one way or another, but a good word like that that's really emotionally charged is ether. There are some people who, if you say the word ether, they will immediately tune you out because they think you're a kook. Period. It doesn't matter what you have to say because you may have a whole totally different concept of what that word means than what they have anyway, and which is another problem. There's a lot of people who use that word and they mean something totally different than what somebody else means. Another one would be cold fusion. If I said cold fusion, you'd immediately immediately just tune out or tune on. There are some people, if you say ether, boy, they are ready to start, genuflecting. I mean, they're ready to start worshiping because that's a word that charges them, and it doesn't matter what you say, they're going to love it. So we've got this word, but another word, at least in the NPA circles, would be the word relativity. If you say the word relativity, there's several reactions. Some people are ready to go to battle because they hate Einstein and they want to go to battle. And it doesn't matter what you mean or what you say or what the word means to you. And then there are other people who may tune out and say, oh, this is something I can't understand. And so they're going to immediately not listen not because they hate the word, but because they think he's going to talk about something I'm not going to be able to understand. And so they immediately tune out. And so some of you may have that emotional baggage, but just be aware of your own emotional baggage with relation to some of these words. And I will try to use words that don't trigger responses that are going to be negative. But also just be aware of that in yourself, because it is impossible for me to totally avoid that with everyone. But anyways, just again, limitations of languages. All right, so what we're going to do now is play a little game. And I said earlier that we want to talk about a natural philosophy, what it is that we do when we create a natural philosophy. So what I want to do is kind of treat this game, if you will, as kind of like a scientific investigation, and like a criminal investigation, excuse me. So if you are, if you're an investigating policeman and you're trying to figure out what went on with a case, you're going to ask who did it, what exactly did they do, when did they do it, where were they or where did they go when they did it, and how did they do it? Yeah?
Great, great. That's a good place to stop and say, what 5 questions are you going to ask?
Well, it's already on the outline, so they'll have that. But okay, fair enough. There are actually 6 questions that you would ask. Uh,
You should,
Hang on.
tell them not to, tell them with the outline, only look at the first page.
Well, we're going to use the second page in just a second here. No, I can change it.
When you give out the outline, so this is something you do so it's more engaging.
Hmm.
So, because when otherwise, if you keep talking, so really, what I learned at Cambridge is so useful. Is so you, that's it. That's something where you can gauge them. That's easy for them to answer and ask them. So, what are the 5 questions we ask?
Okay.
Well, it's on the first page there. So
All
this
right.
is
So, what are the 5 questions or the 6 questions that we would ask? It's on page 1. Go ahead and look at it.
no, 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 no. Take it off there.
Just put in fill in the blanks. All right.
Yeah,
Okay. Sure. Fair enough.
and tell them only look at the first page.
All right, look at the first page. Tell me what those 5 questions are. Yeah, I do occasionally use fill in the blanks, so that's fine. I can do that.
And can we? I'll wait while you do that if you want to stop the recording and
No, I'm not going to do that. I want to try to get this all in one. Let's try to get some flow to it.
so you should take off C back and take off who, what, where, when, why.
Okay,
Scientific investigation, answers to basic questions.
fair enough. All right, I got that in the recording, so I'll remember that. All right, so we ask who, what, when, where, and why. Now, I just want to point out that science really doesn't answer the question why, but we can get good answers to who, what, when, where, and how. And so what I want to do now is take a look at the back of the handout, and I got a little game here: who, what, when, where, how, and why. And we're going to try to look at these 6 questions in several different ways. Now, I'm beginning with Genesis 1:1. It's a common scripture. In the beginning, God created the heavens and the earth.
Okay, so stop there. This is another way. So you're, if you want to draw them in more, have so many people have memorized that.
Sure,
Instead, tell them what is the first sentence in the Torah,
sure.
and they'll figure it out for themselves. So
Fair enough.
take that off as well.
All right, we'll do.
So
In the beginning. All right, so tell me what the first scriptures. All right, so can we write those 5 phrases in the beginning in the first 5 blanks of the first line? In the beginning, God created the heavens and the earth. We're going to leave the last one blank. Okay?
So wait. So this is the teaching the way we do at Cambridge takes more time, but speaking from 11 years, your people are with you every second of the way. You have them waiting for the answer. Like with my students, I would have them. Um, we call it edge of the seat teaching, where
Okay.
they would be
All right.
And so with the scientific investigation, again, I think you should take off who, what, where, when, how, because they're going to have to write it in the
Well, they're going to
first.
write it in the line two. That's the question.
Right, but you shouldn't even have it there. Have them so they guess that, which is easy. Give them easy things, and
Okay.
then have them work. Give them a few moments with a partner
Okay.
to write
By the
in.
way, I want you to print this out. Do you have it printed out?
No, I don't
I
actually.
want you to do this with me now because we're going to fill this out and I want you to see.
Okay, I've got my.
Can you do it and just take a minute to do it? Because I agree with everything you're saying. I just thought we ought to have something in there at least. So, because there's going to be a lot of things we're going to fill out. So there,
Right, but we start with the easy. So
I got it.
this,
All right. So they can put in the beginning, God created the heavens and the earth. That's five.
and they have to figure that out. They're going from
Well,
there, so you've got them. Because even those who don't know the Torah have an idea of that.
okay. It's just okay.
It's
But
just
there's six blanks, but there's only five. We're only going to do five of them for some and six for others. So I thought it was clearer to just put it in there.
no. You can just tell them the first is 3 words, the second is 1 word,
All right.
the third
Third is
is
one word. Second is two words. Well, I can just put in how many words.
right, and also this is important.
All right. Well, they're going to be plenty engaged. I want you to be engaged. Now, your homework is to put in a question, one of the six questions for each of those phrases. Now, the one I'll just tell you, one of those is ambiguous, and I'll tell you which one it is. What could be interpreted in a lot of ways. So do what last.
Okay, just a second.
All right. Do you have it physically printed out?
No, I can't. My printer doesn't connect. I'm writing it out in my
All right.
worksheet.
Fair enough. So I want you to tell me which question goes with which phrase.
Tell you right now.
Yep.
So
So in the beginning,
when,
correct. God
who,
created.
what?
Yeah, that's the problem. What is ambiguous? There's another word that really goes there. Yes, created. You could say what could go anywhere. What
It
is
could be how.
how? How is a verb. Okay. And then the heavens. That could also be what, but it's really not what. Do what last? Could it be anything else? There's only two words left. Well, there's three. There's why, where, and what.
Well, it would have to be where then.
Where? Because where couldn't be anything else. And the earth. That's
That's not intuitive.
okay. Let me put it this way. In the beginning, God created a place and
Oh,
stuff to put in the place. He created this. He created space, and he created stuff to put in space. Okay, so he created a where and he created a what. The what is the earth. Okay, what's missing is the why. It doesn't tell us why. So that goes in line six.
okay, that's really good. That's good. You just taught me something.
That's why I said what is confusing. People have created because what could be the action? It could be all of these things could be what. So and everybody put what in all sorts of different places. So that's why I say do what last. Okay.
That's good.
Okay, so we understand that. That's basically, if you will, that's a natural philosophy right there. It's telling us who did what, why. So let's think about now what secular. I probably should put grammar next. Let's think of this in terms of grammar, because these questions, there are only six questions, and the question might be why aren't there seven, or why aren't there just four or five? Okay, why are there six? And it's because there are actually six parts of speech, six ways in which we can put a sentence ultimately or a phrase together. In grammar, this in the beginning, which is a when, that's an adverb, okay, or an adverb clause. God is the noun, but it's the subject. Okay, so the who is the subject. The created is which part is, I shouldn't be telling you, I should be asking you. What part of speech is created?
Verb.
Verb. Okay, so we've got the noun and the verb, or the subject and the verb, and then what's heavens?
Object.
The object, which is also a noun. Okay, but actually we're treating it as created. It could be one way to think of it, created in the heavens, where, in which case it would be also an adverb.
Yeah.
And then what he created was the earth. Okay, so he created the place to put the earth, and then he created the earth. So in a way, we can think of that as an adverb. So anyway, that's basically the parts of speech that we can have. And then why did he do it? That would also be an adverb if we did that. Okay, so basically that's all the parts of speech, and that's why there are only so many questions that we can ask, and there's a limit to these. And this number of questions is important. Like I said before, science doesn't address the question of why. But now let's talk about line 2, and I think I'll switch that order. Line 2 is the secular. What is the secular answer in contrast to these questions? So secular would say, instead of in the beginning, would say what?
The Big Bang.
Okay, at the time of the Big Bang. And then instead of God, it would say what?
Um, it just happened. The
Okay,
nature.
nothing,
Yeah.
or random, maybe random chance.
Yeah.
Okay, so at the time of the Big Bang, nothing. And what did it do? Did it create?
I need to get this call. I'll be right back.
All right, I'll pause. Okay, I unpaused. So we're back at the little handout here.
Yes.
And the question was, so we have, instead of in the beginning, we have at the time of the Big Bang. Instead of God, we have random chance or nothing. And what did it do?
It banged.
It exploded. Okay, yeah, sure. And it exploded into what?
Well,
So in the beginning, so at the time of the Big Bang, nothing exploded. Where?
oh, this is good. Nothing exploded everywhere.
Nothing exploded everywhere or into space.
Nothing, but everywhere.
Yeah, yeah. Okay, nothing exploded. And what exploded into what? What did it become?
Something.
It became something. Yeah. So secular science would say, at the time of the Big Bang, nothing exploded into space and created everything. Right?
That's good.
What about, let's talk now. Some of you may have a New Age background or what I would call an Eastern philosophy, but it's a different way of looking at things. How would they answer this? How would they look at this? This is a different worldview. So instead of in the beginning, I think most Eastern philosophies would say there is no beginning, right? So forever, since forever, and
Great, great, great.
yeah,
Just so you know that the Skype stopped a few months ago and then started again a minute ago.
okay, but that doesn't make any difference on the recording.
Okay.
Recording is still going on, so it doesn't matter.
Good.
So again, what would it? Let's think about Eastern philosophy. Instead of in the beginning, would probably say what?
Vishnu or Krishna.
Okay, so you're answering instead of God. Instead of in the beginning, what would you say for the when?
Eastern philosophy, I don't know what they say.
I think most would say forever and ever because it's ongoing. Everything is in cycles and it's never does. There is no beginning and there's no end.
I get it.
And God or nature maybe or all that there is or the one or Vishnu, Krishna.
It's,
Okay, different views. There's not a right answer here. Just trying to get a different view. And what does it do?
well, I hear that these different gods, they'll say that they made them.
Okay, so there is some created but also destroyed since it's going on forever. It's just cycling.
Yeah.
It's not really creating ultimately. There's no creation. There's only recreation and recreation, right? There's no creation. Not in an ultimate sense.
Yeah.
Okay, and where? I guess you might say, I don't know. Instead of the heavens, they might say what?
Well, in the Egyptian
Okay, so it creates a woman's body. I guess I was thinking my idea of what Eastern philosophy would be the universe or the total the place of everything, but also consciousness.
And they talk about a oneness.
So
That
yeah,
everything's
created it, but God created in the mind, really. So in other words, it's none of this is real. This is all in the mind. So the where is in the
this
mind.
is okay. I'm listening. This is
Okay, it looks like we're right where we left off. I had a little break there. So we were talking about the Eastern philosophy, and I think the point is the sentence should read uh, so instead of in the beginning, we have forever and ever the universe or nature recreated in the mind whatever there is, all reality. So that would be more or less the Eastern natural philosophy. And again, we can get different flavors of this, but the point is these are three, fundamentally different ways of looking at how the universe operates, and that is going to affect how we're going to look at our science. So what I want to do now is move on to these basic concepts. And Natalie, I know that you've already answered these before, but let's just take the time to ask these questions for the next line, which is the concept line. Um, and I think it's rather than just try to ask you and have us guessing all day long, I'm just going to give you this line, but I'm going to ask you questions on this on the last line, which is units. So the concept that we want to associate within the beginning or when obviously is time. That's a pretty easy one. The concept of who or the subject or what is making things happening, what's driving science. Most people, I think, would probably say matter is what drives science. And I'm going to challenge that and say what I think is driving science is relationship. Relationship is what goes in that second blank. And what does relationship do? It moves. It moves things. Okay? So that goes in your third blank. The third blank would be motion. Okay? So we have time, relationship, and motion. What does it move? Well, I'm going to skip a blank here, and we're going to do under the what or under the and the earth. That's going to be your answer to matter. That's what. Whatever matter is, that's the stuff that exists. Okay, and where does it do it? In space. So we have time, relationship, motion, space, and matter. I would probably switch the order on that, but that's the order that we had in the original sentence. Okay, so those are the five fundamental concepts of science. Again, we don't really have anything that connects to the concept of why, except possibly intelligence. Intelligence is giving us an answer to the question of why. How we make an equation out of intelligence, I don't know. But that would be interesting. That's something for definitely for us to be talking about in the future. But that'd be where the why goes in that sixth blank. But we're going to not really spend time on that. We don't have a unit that we can associate with intelligence. And when I don't mean an IQ, but I mean it's something we can measure. So that's the next line is we want to, and I need your help. What unit, and when I say a unit, what I mean is something we can measure for that concept and not a particular unit. So for example, a coulomb is a particular unit of charge, but the concept, the unit itself is charge. Okay, the unit system independent value is charge. That's what I'm looking for this next line. So what would the unit of time be? Well, that's a little confusing because the unit of time and time are the same word. That's that's not too bad. So we just have time for both. And in fact, for space, well, space is three dimensions of what? Of length. Okay, so those are the easy ones. Time and length are the unit that we can measure. What is the unit of, well, let's try this in a different way. The unit of relationship. You want to make a guess on that one? Are you there?
I didn't write it down and now I'm forgetting.
You forgot the unit of relationship?
Yeah, I just remember charge.
Charge is not the unit of relationship.
Right, charge is and the earth is charge. Energy, energy.
Energy, good, yeah. So some of the guesses that we might get, would be entropy, I think was one you gave. Um, and of course, some people think, mass or matter would be one thing. So that's the unit of relationship. Okay. All right. So we've got two more to go. We've got motion, we've got the unit of motion, and we've got the unit of stuff or matter. Okay. So what do you think is the unit of motion? Remember, it has to be independent of the other units. I didn't say that, but
Temperature.
that's too easy. You knew the answer. Most people, I think, when we're asked to guess what is the unit of motion, will say velocity. That because we think of velocity as something moving, but we've already defined time and space. Time in terms of time and space in terms of length, and length per time is velocity. So if we had motion in terms of velocity, it wouldn't be independent of time and space. Everybody clear on that? So if we want motion to be something which is independent of time and space, it has to be something else. All right? Other than velocity. And the other problem with velocity is it's a relative measure. We don't know, we can't say how fast something is moving except in relation to something else. So we want something that automatically takes into account the something else. Okay? And that measure, you already said, is temperature. Temperature of a whole bunch, if you can imagine a whole bunch of atoms or electrons moving around, as they're moving around, they're moving relative to each other. And the more the relative motion, the greater the temperature, the greater the amount of motion. So that is really a much better indication of true relative motion than velocity. Is everybody with me on that? And it's also independent of time and space. It's not energy, it's not time, it's not space, it's an independent measure of motion. And that's what we're after. We have one more thing, and that is a measure of matter. Now, Natalie, you know the answer, but suppose you didn't. What is it?
Charge.
Charge, that's right. But I think most people, when asked that question, would say mass. Okay, they would think of mass as that's what stuff is. Okay, we know that stuff exists, and we know it has to be something. But the problem is we already have a measure of velocity, time over space, and we know that velocity squared times mass gives us energy. So if we have energy and we have velocity squared, we already have mass. Mass would not be independent. We need an independent model. And it turns out, and we'll show later, that the concept of charge is the best concept of what really is stuff. Now, don't want you to have a limited idea of what charge is. In other words, we know that there's positive charge and there's negative charge. Actually, I don't believe that. There's positively charged particles and there's negatively charged particles, but there isn't actually stuff called positive stuff and negative stuff. We'll talk about that later. But there is just stuff which behaves as what we call charge. So we need to refine our idea of what charge actually is before we can accept that, because then suddenly we have stuff and anti-stuff, and that's not what I'm suggesting. Okay, there's only stuff, but we'll get there. And it's very much like charge, but it's not quite charge as we understand it. So let's just leave it at that. Move on. So what I want to do then now is move down to this chart I've created.
So before we go to the chart, I have a question.
Sure.
Are neutrons real?
Yeah, sure, absolutely. But they're not. They're a composite. In my mind, neutron is not is a system of a proton and electron that form together to make something which is neither one nor the other. So, for example, when a man and a woman get married, they become a couple. The couple exists. It's not something that exists. I mean, they both change to become part of this new thing called a couple. Okay, and in a similar way, that's what a neutron is. It's not just a proton and an electron. It's a modified proton and a modified electron that come together to create a new equilibrium in this new configuration. Then we could call a neutron. And it may behave differently inside the nucleus when it's coupled with other neutrons than it does when it flies outside of the nucleus and becomes a free neutron. And in 15 minutes, on average, it will disintegrate back into a proton and electron. So that's the answer to that. So what I want to do now is, I mentioned that energy is kind of the...
Wait. I think it's useful, because I didn't know that. I think it's useful when you say charge and you discuss that explained about
Yeah,
particle charge. Can you also explain about the neutron? Because I didn't know you just said that neutrons disintegrate into
sure. I've only got 45 minutes, and I'm up to 40 right now. So
okay.
that's the problem isn't having stuff to say. The problem is how to get take stuff out because it's time consuming. I hope that was valuable for you to just kind of get an idea of this is where I want to go with this whole new way of looking at things is at a very fundamental level. And this is the natural philosophy I'd like to suggest. I'm answering these very questions, and I'm coming up with equations that I can quantify and things that I can measure based on these. And I also want to point out that now I have 5 independent units, and there must be exactly 5 because I wouldn't have an independent system if I didn't. There are 5 units that we can measure. It's not a coincidence. I hope everybody's making this connection in the SI unit system. Now one thing you might know is that there are actually 7 units in the SI system. 2 of them are kind of, well, one is just actually a measure of perception. It's the it's the measure of how much light we actually see. It's not really a measure of light energy, and I don't know. It probably shouldn't be included in one of the 7, in my opinion. The second is Avogadro's number, which is just a number, and we could use some other number, and I think we should, to be honest, and just to get from the molecular to the macroscopic view that we look in. It's about 10 to the 24th is a good number to give us, to get us from the molecule to the mole or the macroscopic view. So those 2 units aside, we're left with 5, and they're independent. So we can get all the units of physics we can get by multiplying and dividing and squaring and whatever operations we want to put on these various 5 units. But once we picked 5, there are no more independent units. So there are going to be, if I can associate an equation with each of these, I'm going to have the fundamental equations or the fundamental laws, if you will, of physics. And that's what I'm trying to do here with this chart that I'm showing you now. So what I want to do is take it a step further and say that these 5 laws are can be broken. And I'm trying to do this in how many minutes now? 5 minutes. There's
Break a minute. Just listen. You okay? This is something I learned at Cambridge.
okay.
We have something called. We would always remind ourselves teacher talking time.
Uh-huh.
So, and you do that a lot, and you're saying it's taking a lot of time because you're saying a lot of things that are unnecessary,
Right.
like what I'm going to do now.
Okay.
I don't need to hear that because you're doing it. So,
Okay. I got you. Well, that's why I'm writing the script. That's
so
why we're
in
that's why we're recording this so I can get rid of that stuff.
so in the script, um, try making everything just into statements, not of only statements. In fact, I'm good at doing that.
All right. Well, that's why I sent you the script is to do just that. So please do it. But first of all, I need to get it recorded. Then I need to get it written down. Then I need to. Then we'll need to do it. I agree.
Okay.
That's why we're doing this. Okay. So what we're going to do now is is to take these 5 laws. I'm going to break them down into 4 plus 1. Okay. And the 1 is the concept of energy. And the phrase I want you to remember is that energy governs. Energy governs, or relationship governs, excuse me, relationship governs. And I should probably have a space for you to write that down. That's important. That's like the overall. So what we're going to do now is get 4 different kinds of energy associated with all the 4 other laws, the 4 other questions. Okay? And that's what this chart is you'll see that there's 2 by 2. Okay? And when we do this, we find that there are 2 laws that govern being, that govern what things are. There's 2 laws that govern doing. You see that being and the doing? Let me ask you, is energy a being? Is it a thing? Or is it a doing? Is it a verb? Which is it?
Being.
Okay. Why do you think it's a being?
Because it simply is. You can't break it down into something less, and it's not doing anything until it moves or until it
Okay.
acts. Unless it's a relationship, it just is.
Okay. Yeah. I've thought about this an awful lot, and my answer is it's not really either. It's kind of both, and it's not really either. Um, a relationship, you cannot have a relationship without things existing to relate, and you cannot have things that exist without having a relationship. So the two are hand in hand, and yet if they're not doing something, there is no relationship. So it's kind of both. Okay, and so it really is, if you can kind of think of it as being outside of this little matrix of being and doing it, it's really both. It encompasses all four. There's energy can be all of that. Okay, relationship is all of that. And on the side, you'll notice that we have individual and group. What I mean by that is we can break physics down. The laws of physics, I'm contending, are the same on all scales. No matter how large we get or no matter how small we get, we're going to find the same equations, the same rules that govern what we see. And so that means if we break something down and we break it, the parts down, and we take those parts and break those parts down, is there a limit to doing this? Is there a point at which we get to a part that we can't break down?
We don't know.
Well, if what I just said is true, then the answer is no. Because if it's the same on all scales, no matter what we do, then no matter what scale we go on, we should be able to continue to break it down. Now, there might be a level at which there's a circuit, and that circuit, if you will, belongs on that level, but then the circuit is going to have structure within the cross section as the things are traveling along a circuit. So we're not going to just have, so even there we're going to have structure. We're going to have breakdown of parts within parts at all levels. So eventually we're going to be able to reach a point where we have infinitesimals. And that's what I mean by individuals. Laws that govern the infinitesimal things. Laws that govern groups of things, how things work together, that's a separate thing. So we have the being and the doing of individuals and groups. And they all have a form of energy. So there's the five. Okay? This is kind of giving an idea of what I'm talking about. So the first thing I wanted to, in the upper left corner on this chart, I want to talk about matter, because that's my first. And by the way, I have to make 5 assumptions. Remember, I said earlier that to make a natural philosophy, we have to make assumptions. And I'm going to tell you specifically what my assumptions are. Yeah.
Okay. I know this is very important, so to help you, the first thing is matter. Instead, you said the first thing you want to talk about is matter. And what we learned to do at Cambridge is we pause, the pregnant pause.
Okay.
So saying less. And when there's something the most important, then there's a pregnant pause.
Okay. So the first thing is matter. Yes? All right. All right. I got it. Okay. And here's my assumption. Matter exists. Okay? And in fact, what is matter? My definition of matter is whatever it is, it's the stuff that exists. It's the stuff that's real. Okay, so by definition, matter exists. Because if it didn't exist, then nothing would exist, because that's what matter is. It's the stuff that exists. Okay? I hope everybody's following me on that. So I'm not going to start and tell you matter is charge. What I'm going to do instead is I'm going to say whatever exists, it's going to have to follow certain rules. And then I'm going to say what follows those rules. Aha, it looks like charge. You see the difference? That's different than saying matter is charge. You follow me? Okay, and that's what I'm doing. I'm not coming into this with an agenda. I'm coming into this and saying whatever exists, I'm going to call that matter. And I'm not going to assume that, as Eastern philosophy might have it, that there is no such thing as matter and that everything is in the mind. I'm not going to assume that. Again, I can't prove this. This is something I can't prove, but I have to start somewhere. And where I'm going to start is saying matter exists. Hopefully, you can, if you don't accept that, you can at least understand that. So, and I'm going to say, I can talk about an equation, but basically I'm going to say if I'm going to quantify this, how do I do that? How do I say, I know that relationship, somehow the fact that this exists has to communicate itself to something else, which is over here, right? That's because relationship governs. I started with that. And in order for there to be a relationship, and this is here, and this is necessarily somewhere else, I have to express this relationship in terms of something that's based on the fact that this is here. Everybody with me? And what I do to do that is I have something called a field. Okay, the field is how I express how this piece of matter is relating to everything else in the universe. And it's relating more intensely when things are close because those field lines, if you will, are more powerful, more closer together. When they spread out, they diffuse and they become less important. Okay, so there is a mathematical relationship that I can express. It's called divergence. Divergence is just spreading out, and you can imagine a little arrows pointing out. That's basically my equation for the existence of matter. That the existence of matter is equal to the divergence of a field. Simple enough.
I don't see that written on your
It's
chart
not,
project.
but I will write that out. I'll have that. I'll have a PowerPoint here, don't forget. And I've shown you, and I'll draw a little picture. Here's my little dot with arrows. Okay? So whatever matter is, it has to have that. It has to do that. Now, it turns out if I have two elements of matter, and I'm not making any demands on them at all. I'm just saying I have two elements of matter, and they're just going to have a similar field, and I'm going to define energy, then, or force, if you will, as an interaction of energy. It's the gradient, or the how much things move downhill of my energy, which is calculated at every point in space in this relationship. Then it turns out that force is going to be repulsive between these two elements of matter, not attractive. And what behaves like that? When I have two similar things and they repel each other, what behaves like that?
Two positive charges or
Or two negative, yeah, and I'm not even to the point of talking about positive and negative charge. I'm just saying two things that are the same, that have fields like this, they repel. Aha, that behaves like charge. I'm not saying that all matter is charge. I'm not saying that yet. I'm just saying whatever I just assumed about matter behaves like charge. It doesn't behave like mass at all. Mass would do the opposite. Mass would be attracted, but that's not what these do. Okay, so that's my first hint. This is not mass. There's something else. Mass has to come in somewhere else. Okay, so the law here that I associate with my first question of what, or what am I? This is the object, is that matter repels. Okay, so we've got two so far. We've got energy, or excuse me, relationship. Relationship what?
let me look back at that. Wait, 'cause I have to see it. Relationship, energy,
Yeah, relationship does what?
govern.
Relationship governs. That's the blanket over all of this. And matter, what does matter do?
It just
No, but
is.
what does matter do? Matter does something. I just told you what it does.
It repels.
Yes, matter repels. That's key, okay? Because that's opposite to what we're commonly taught. Now, what about gravity? We're going to get to gravity, but this is at a very fundamental level. We're going to get to charge, but at this point we just got the idea that matter repels. That's our second law, okay? The first of the four. Now we're going to move on to the idea of motion. So we're moving on to the doing of stuff. That was the being of stuff, the fact that something is. And by the way, you'll see several things on this chart. If you look on the chart with me, you'll see the word transformation. What I mean by that is there are only so many things you can do. You probably learned this in grade school. If you have a pattern, you can. What are the things you can do with it? You can move it, you can flip it over, you can expand it, or you can rotate it, right? What else can you do with that? That's pretty much it. Those are everything else you can do combinations of those things, but those are the four fundamental transformations. And there are only four because there are only four laws. In other words, this is not a coincidence. These things necessarily belong together. And the one that I associate with matter repelling is the transformation of reflection. And if you look at this little graph, which you can't see, but it's a dot with the arrows pointing out, you'll see that if you were to flip it over, it looks exactly the same. Another thing that's interesting about it is there's something called Noether's theorem. They're saying that if you perform some operation on a system and the system remains unchanged, so if you were to take a system and flip it in the mirror and it looked exactly the same after you flipped it in the mirror, then something is conserved. The thing that gets conserved is charge. Because that would mean that if right-handed and left-handed are having to do with right and left-handed motions, which we'll talk about in a minute, then the right and left-handed motions would also get flipped in the mirror and they'd be exactly the same, so charge would be conserved. So this is related to that also. Another thing is in grammar, We have the word reflexive. A reflexive verb is like I'm going to buy me a dog. The me, I'm going to buy to myself a dog. It's always reflecting back to the subject. Okay, so even the idea of reflection itself has to do with the idea of identity or existence. So reflection is definitely the one uh, to to associate with the concept of identity or existence.
So I have a quick question.
Yeah.
Can you quickly review how we know matter repels? Not talking about charge, but just matter repels.
Well, again, it has to do with if I set up this concept of field, and I've got these fields going on, and then I take another one, and it's doing the same thing. So I've got two of these. The interaction of these fields at every point in space generates a function. It's an energy density function, and there's a value for that function everywhere in space. Okay? Can you kind of, and I could draw that out. In fact, I will draw that out, and you'll see that it's denser in the space between them, and obviously as you move out, it becomes it goes to zero eventually. Okay, so that's the energy density function. Now, if I take that function and I look at it kind of like a topological map, okay, except in three dimensions. So I've got hills and valleys,
Yes.
okay, and I say overall, I'm going to integrate. I'm going to add up the slopes of this map. So what is this map doing overall? Is it tilted, or is it overall flat, or is it overall tilted this way? You see what I'm saying? If it's overall tilted in one direction, that's called a force. That's the force that's acting, and the tilt depends on which one you're doing. If you're acting one on the other, A on B or B on A, you're going to get opposite values. So the tilt will be this way or that way depending on which you do. And I'm not going to do the math here right now, but if you do the math, you will find that there is a tilt, and that tilt is moving those particles apart.
So Greg,
Yeah.
what you could have just said to make that quicker, if you do the math, or just simply the math shows that da 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 da. I said I'm not going to do the math right now, but if you do the math, da, da, da. So
Okay.
the math shows.
All right. I'll just say the math shows. Sure. Fair enough. But anyway, the image I want is the image of the hill. The overall tilt, that's the force, okay, that acts between things. That's what you need to get in your mind. And the energy density then is this function that's all over space. It's not just a two-dimensional, but a three-dimensional function. Make sense?
Yes.
Okay, so that's where that comes from. And I'm not just making it up. I derived it. And also from that, I can derive the law, Gauss's law, which is basically just another form. There's different forms of it. This is one I just showed you, the differential form. I can get Coulomb's law from that. I've shown conservation of charge. This is the energy. The energy that I associate with this is the energy of potential. Because something exists, it has potential to do something. It doesn't. It's a being, right? It's not a doing. It hasn't necessarily done anything. It's just because of it's there, and that's of course potential. Then would be charge, which is the constant E times voltage. Voltage would be potential per charge. Okay, so that's the energy. There's an energy associated with each of these four, and this is the energy of position. Okay, and we can talk about the personalities. I'm going to again for time. We'll maybe save that for later. Let's talk about motion, number two. This is the doing of individual things. And what we want to talk about is the concept of attraction. Where does attraction come from? Well, it actually comes from
Wait.
motion.
So wait. So this will come out in a edit, but what we want to talk about is motion. Just motion
Okay.
tracks.
Okay, but I'm saving that until I've actually shown why motion attracts. But maybe I should say it first.
No, but you were saying what are we going to talk about?
Okay, we're going to talk about motion. What does motion do?
Just say motion.
Motion
What
attracts.
okay, this is how we learned it at Cambridge. You know when you have a oh you do have a dog, and you say and not a rather unintelligent dog, and you say, what's your dog's name again?
Boo.
Okay, so oh you're such a good dog. I just love the way that you carried me my slippers, and just forgive me that I'm going to give you a little cookie. Boo, here's a little doggy cookie. Boo. So all the dog hears is his name.
Right,
And for us, we're trying to listen for what's important.
right.
So
It's all important. I wouldn't say it if it wasn't. But
what's not
okay.
important, what's not important is we're going to look at this next. It's
Yeah,
you do this, or that's not important, and it's exhausting.
I see.
And you'll see that once you self edit, then you have lean language. And the lean language for the listener helps them absorb what you want them to
Right.
absorb.
That's why I want to write it out. That's why I want to have the script. I understand.
So what I
So
would
what I need to do is put pauses in there. Just put dot 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 for a pregnant pause or something.
yes, and what you're
So I
learning
need you
is
to help me do that.
yeah, I can coach you. And what happens is you speak when you're teaching, you're not having a discussion.
Right.
You're not filling in blanks. In fact, when I was as an instructor, many times there would be a pause in the class of a full minute. And
Okay.
when I asked a question, when people were thinking, I would walk to the class so they couldn't see me, and I would wait.
Hmm.
And it's in that waiting that the person's mind catches up with yours
Right.
and they give you the answer. But trying to fill in the blanks for them is confusing and exhausting for the learner.
Okay.
So I
So, all right. I basically I've given 8 hours of talk just on this chart. So how do I condense it into 10 minutes? It's frustrating.
I think I can teach you how to do that once I understand the chart more. We can do that next time, Greg.
Okay. But you understand that's what I mean, because this is what, again, I think I've given you. This is a natural philosophy. I'm kind of giving you mine, but there's a lot to this. This chart is a lot. I mean, I can't say it strongly enough. This is not just some nifty little chart. This is the basis for understanding physics right here.
This is what I understand, and this is why we want to get this into our book.
I understand, but I'm just trying to say I can't do justice to it in 10 minutes no matter what I do. But I'm trying, but uh,
Okay, so
I'm giving an overview because I'm going to come back to some of these things later. It's not like I'll, just saying them once, but all right.
so we were on doing.
Okay, so motion attracts. And as you recall, the concept we want to associate with this is the concept of space, which has the unit of length. And so you might wonder, well, how is it that motion attracts? Matter naturally repels. There's got to be some way that we can get attraction, or we wouldn't have, right? We wouldn't have a physics. So what is that?
Charge.
No, it's motion.
Oh, okay.
Okay, it's motion. But how is motion do that? Okay, and here's all we need to think about is water flowing through a hose. Okay, so you now put your finger over the end of the hose, not to totally muffle it, but to let a little stream out, right? So you can squirt your friend. You've all done that. What happens to the stream of water that exits the hose? Is it slower or faster?
It's faster and it goes in different directions. It diverges.
Okay, it diverges. That the fact that it diverges isn't important, but the fact that it goes faster is very important. What if you instead just had a pipe and you had water flowing through a pipe and then the pipe constricted and then it expanded again? What would happen in the
When it
constricted part?
constricts, the water would flow faster. When it expands, the water would flow slower.
Right. And why is that?
Because the same amount of water is keeping to travel in a smaller space. So it has to, if it's the same amount of water, it has to move faster to get through that smaller space. And vice
Yes.
versa.
Yes. Because the amount of matter that passes through each given cross section is neither created nor destroyed, right? We can't just
Right.
we don't just get suddenly more matter because it went through a smaller cross section, right? And that's there we go. That's my second assumption. Matter is neither created nor destroyed. Matter is conserved. Because matter is conserved, motion attracts. Now let's reverse the logic here. We know that when you constrict a flow, it moves faster, but we can also reverse it. If the flow moves faster, or excuse me, if the flow moves faster, then it constricts. It works both ways. Okay. So let's take a look at a waterfall. If a waterfall, when the water is flowing out at the top of the waterfall, is it going faster or slower when it gets toward the bottom?
Faster.
Okay, because of gravity. So if you were to look at the cross-sectional area, now it may break out into several branches at that point, but if you were to just look at the total cross-sectional area at the bottom, would it be greater or smaller than the cross-sectional area at the top?
It must be smaller.
It must be, right, because if it wasn't, there'd be matter would be created or destroyed if it's moving faster. Everybody following this? Okay, so if we have a flow of, let's say, a river, and the river is going through rapids and it's moving faster, then
Okay,
it's,
Greg.
yeah.
So this is what I'm realizing you're doing when you say everybody following this. Okay, so that let's pretend you're in front of your class.
Hmm.
So you say what was really useful to me about the waterfall and the water falling faster at the bottom, and therefore it must have the water must take up smaller space.
Right.
Then you're quiet and you watch your learner's eyes and their body language
Okay.
only, and if they don't understand, they're going to put up their hand or say something.
Sure.
But you're saying everybody understand that they're imagining that you're interrupting their thoughts.
Okay. So what should I say? Nothing at all?
Nothing. So much of our speaking at Cambridge, when I learned to speak, much of it was silence and watching the body language
Hmm.
of. So this is why I won't get into it, but this is why when I saw so but remember I'm the child of two different cultures.
Yep.
So I watch body language perhaps more than the average Joe and I've lived in 5 countries. So I've lived in countries where the language was my second language or
Hmm.
third.
Hmm.
So body language perhaps is something I'm more aware of than most people. I feel people I found out that I feel people more than other people do. So um, in your as an example, when I figured out what Henrik's raison d'être was, which was nonverbal, um, then that's when I started withdrawing from him. But you have no idea, even from his letter. Um, so that's something that I do more than you, and it's perhaps because I'm a woman, but also because of my upbringing.
Yeah.
And this really helps in teaching.
Okay.
So that's why I've been told I'm a good teacher because I don't say a lot. I watch and I come in, I facilitate only when I see there's a gap in um, in understanding. And also, I'm watching really carefully. I'm watching discomfort, like if they're jiggling a foot.
Sure.
I watch if they're relaxed, then they're learning.
Right.
And
But I don't. If somebody jiggles their foot, I'm not sure what I should do. You jiggled your foot. Quit jiggling your foot.
no, it's so this is good that we're having fewer learners because this will teach you a new relationship between you and the people
Okay.
by watching them.
Sure.
And you can tell a lot about someone's character by watching them.
Sure.
And this is where there's a gap between you and me when we discuss other things, and why from that also I can really sense sickness in someone. I have a new client now who has cancer,
Hmm.
and we're only working by contract.
Right.
So she has to obey the contract, go by the contract. If the contract's broken, I'm not going to work with her anymore, even though she's buying the Kangen technology. So I'm in making the contract. We're going to Skype, and I'm going to be watching her when we Skype to see her comfort level with this contract.
Hmm.
So I use this a lot since Cambridge and since teaching for 11 years. I use those skills a lot, and you can see that I have to grow into what I'm doing. But I did learn some things correctly, and that is only 10% of what our communication are our words anyway,
Right.
and I depend on the other more than the words.
Fair enough. All right. I want to learn to do that. I do.
So it's silence and being comfortable with the silence as you watch your learners, and being comfortable with moving to the side of the room sometimes.
Sure.
And so in my learners, they're the focus.
I
So
gotcha.
I'm not so much of a speaker as I was taught to be a facilitator.
Okay. All right. I'll try to do that. That sounds great. I just, how I actually put that into practice is still not clear, but that's good.
This is what we'll do. Sometime before the end of the month, I'll do one of my teachings,
Okay,
and I'll be teaching you because it'll be new for you,
sure.
and then you'll see the difference.
Good enough.
I'll
Oh,
model it for you.
fair enough.
And you don't see this type of facilitation very often because, unless you come to my classroom, because it's a skill that only some speakers use.
Okay.
And
Well,
good speakers and or teachers, you'll notice that they all will say less and they'll all have pauses.
yep. I will. I want to do that. That's why I want to write out the script so I can do just that.
Okay, so we'll practice.
All right. Good enough. Should I go on?
Yes, because we're going to complete this.
Yeah. I don't know where I was, but
So you were on
I know I'm somewhere in number two, motion attracts. We were talking about rivers and pipes and various things. And so the point being, when something starts to move faster, there will be a constriction. We see this in all sorts of things, but one place especially we see it is with electric currents. We see it with lightning. Lightning moves very fast, and the faster it moves, the thinner get for the same amount of matter, the thinner will be the strike. Okay, and we see it. That's called the pinch effect. So we see the pinch effect in electricity. We see that idea of motion attracting. We see it all through space. We see it, I believe, in elementary particles. We see systems of things moving, and the fact that they're moving once they start, which is obviously moving at all, is faster than not moving. So that there's a motion inherent in the fact that they're moving.
I have a question. So in the Birkeland currents, when we have nodes, the electrical flow is the charges are moving faster at the node?
No, we're going to get to nodes later. Nodes really have to do more with law number the next law, which we're going to get to. This is just the fact that just because there's motion, there's attraction. And it's really as simple as that. It's as simple as the fact that the motion demands, because there is the same amount of matter, because matter is conserved, that's my assumption, the same amount of matter has to pass through the same cross section, then there must be a same amount of flow. Right, the same when an increased velocity has to increase, has to pinch. So motion attracts. It's a very simple thing, and we see it. It's not just electricity. We see it in other things too. We see it in the Bernoulli principle. You've seen it with your shower curtain. When the water flows down the shower, what does the curtain do?
It goes towards the water.
It goes towards the water, right? Because the water is moving faster than not at all, okay, which is moving it in. What about if a really fast train goes by? What could happen? And you're close to it.
If then you get sucked in.
You could get sucked in. Yeah, literally. I mean, fast enough, it could actually be dangerous. I don't, I mean, seriously. Also, these laws are mathematically. I'm not going to do the math right now, but you can get Kepler's third law from this, and Newton's second law, F equals ma, all come from this basic idea we can quantify. Here's the important thing as far as both of the motion laws, both of the doing laws. We have a time change. Okay, we have something changing in time, motion, velocity, and we have a spatial change, a pinching. And the spatial change and the time change are related to each other. That's how these laws have to work. They couldn't work any other way. And because time over space gives us velocity, what is that velocity? Well, it's what we call c. And some people say, oh, that's the speed of light. I don't like to call it that because we'll talk, I believe it's the speed that matter has to move to maintain itself. Okay, so this is a special speed, but we see this with both of these laws, and that's because time and space work together. It isn't because time is another dimension of space. It's just because we can't separate the two. We're going to have, when we have a change in time, we have a change in space at the same time. Is everybody with me there? Okay,
So
we're going
what you would have done there is when we have a change in time, we have a change in space.
to, gotcha.
Silence. Not
Okay,
everybody would be there.
yep,
Silence. You
gotcha.
look in their eyes, and if you see they have furrowed brows, then you don't speak again. You say,
Okay. What's on your mind?
Yeah.
Okay. All right. This is a new habit. It's hard for me to work on that. At this point, I could say one more thing, and that is let's think about motion of the planets going around the sun. If they were to, if the Earth were to suddenly start going faster, what would happen?
Then it would have to get smaller.
No. If it just started moving faster than it is right now, it would.
It would move. It would get to the sun. Its orbit would get in relation to what the other planets. If it moved fast enough, it would suck the other planets in.
Yeah, the Earth isn't going to have much effect on the other planets. It's pretty small. Um, no, I'm just looking for something real basic. It would start to spin out.
It would move faster. It would spin out of its orbit.
Yeah, it would spin out just like if you were swirling a discus around, on a string, and then you let go of the string. I mean, or spin it faster. Eventually, it would there'd be more outward pressure, right?
Yeah.
Okay. My point here is that the ultimate motion, we can get a little confused, okay, because it seems to be doing just the opposite. What I just said was that motion attracts, but here increased motion would make it spin out, okay? And if the Earth were to slow down, what would it do?
Go more in towards the sun.
It'd spiral into the sun, wouldn't it? So my point is, when you're dealing with mass, okay, the opposite of what I just talked about, it takes place. Okay, so that can get a little confusing, but at the fundamental level, at the level of actual motion of particles, this law of motion is what holds, and it makes sense and it's logical. So don't get confused by that. We're gonna talk about where gravity comes from in a little bit, but I just want to make that little point there that that is the opposite of what you'd expect based on this law alone.
So
Okay?
just to show you there, you don't have to say, I don't want you to get confused.
Okay,
Just say it, wait and watch their eyes,
gotcha.
and then we're going on to gravity.
We're going to go on. Okay, we'll talk on that in a little bit. Number three of the four. Circuits separate. Okay, the idea here is the idea of quantization. What's quantization? Quantization is where does the land begin and the sea end? Where do I begin and you end? Where does one thing start and another thing ends? That's quantization. That's how we know. In other words, how does something have identity at all? Where does that come from? Circuits define how that happens. That's what we're going to talk about next. And circuits assume motion. You can't have a circuit unless something is moving, and that motion not only moves out but eventually comes back. Because let's think about this. Circuits are a necessary consequence of things being finite. If I have a ball of stuff, and this ball of stuff, I know, or I'm assuming I know, is held together by its own internal motion. Okay, there's motion going on, and these motions are attracting each other and keeping this ball fundamentally in place. Then that motion cannot go on forever, can it? Because I have a finite amount of space. It's only so big. Eventually, this motion of however it can be all kinds of knots and really complicated circuits, but eventually it has to come back into itself, does it not? Because it's finite.
Yes.
You with me?
Yes. You don't have to say it with me.
Yeah,
Just
okay.
in their eyes.
All right. So circuits are necessary. You cannot not have circuits. And circuits define things. Let's think about, we've talked about this, I think, in the first lesson. Let's think about a whirlpool. Okay. When there's a whirlpool, you've got something swirling around. Okay. Now, does the whirlpool exist?
Well, we're talking about the motion, for that we're using the word whirlpool.
Right. Okay. So the whirlpool, in a sense, doesn't exist. It's the motion of what exists is the water or whatever it is that's, whatever the medium could be air. something is circulating, but it's the motion that we're talking about. That's the whirlpool. That's the circuit. That's the thing that's existing. So it's a group thing. Okay, remember before we were talking about just the existence of matter and the existence of things and the existence, the motion of matter. Now we're talking about the existence of groups. What is the group? The group is a circuit, and all circuits have a center. Everybody,
All circuits have a center.
all circuits have a center, and the center defines where it is, because a circuit isn't in just one place. It's a whole system of things moving together, working together, but it has a definite center, a definite point that we can say that's it. Okay, so that's how a finite amount of matter can coalesce to form quantized groups of things. Okay, circuits are what separate one thing from another in the most fundamental way. That's the basic law behind this. And this is the law, the equation that we have that governs this is actually the simplest and most beautiful in my opinion. It tells us that a magnetic field doesn't diverge. And what that means, one way to interpret that is to say that when they don't diverge, that means that they have to eventually wrap back into themselves. The magnetic fields themselves must form circuits. So the motion's forming a circuit, the magnetic field is forming a circuit, everything is forming circuits. That's what it means to not diverge. It doesn't do remember when the first law we said if we have something that exists, it diverges. The field diverges. Magnetic fields never diverge because there's no such thing as a motion iton. Okay, there's some people that may argue with that, and that's part of their natural philosophy, but I'm suggesting that that's not the case. The magnetic field is the field of motion. It turns out that mathematically we can deal with a magnetic field in many ways exactly the way we deal with an electric field, or the field of matter and the field of the motion of matter can be dealt with in ways that are compatible, and they are exactly the same, and that's beautiful. But fundamentally, they're different things: matter and the motion of matter. You can't have one without the other, but they're not the same thing. So this is the law that governs motion of groups, and that's where I would associate the idea of temperature. And this is an interesting thing. Also associated with temperature is the concept of entropy, because it turns out that entropy times temperature is energy, and energy is what governs. Okay, and so we've all heard the second law of thermodynamics, which tells us that entropy always what? What does entropy always do?
Well, it's where the whole universe is going, supposedly towards entropy.
Yeah, well, no, it isn't going towards entropy. Entropy is increasing or decreasing.
Increasing.
Yeah, entropy is a measure of randomness. There's a lot of different ways to interpret entropy, but one is to say it's how much randomness. So there's another term called negentropy, which is order or organization. Okay, so they're opposite, but entropy would be disorder. Okay, and that was just, again, that's a convention. Somebody could have decided to call entropy a measure of order, and then we would be using it the other way. But that's the way the word has been used historically, so we're stuck with it. There are people that use the word negentropy.
So great. So am I correct? The only thing in the universe that self-organizes, self-corrects, and self-sustains is electromagnetism.
Um,
That we know.
that's just too simplistic. I don't. No, what we need to understand is what causes things to do that. So no, I wouldn't say that, but I will say that electromagnetism, the laws of physics ultimately are electromagnetic. So how can you talk about there being anything else? I mean,
Because we have to define it to someone who, and we're getting back to better sheet again. So Hashem created everything through electromagnetism, light,
hmm
and electromagnetism. I get that the laws of physics are about electromagnetism. Although Joe Blow down the street wouldn't say that, but electromagnetism, by definition, um, self-organizes, self-corrects, and self-sustains.
Hmm.
And it's the only, there is nothing else. I know you're saying, but there is, this is, I'm saying something that's obvious, but there is simply nothing else because there is nothing else. Everything is part of electromagnetism.
Hmm.
But it is what orders the universe, and that's why Hashem created it on the first day. So I
Okay.
don't see another way, even though there is nothing else. Yes. So that we could say another way. There's only electromagnetism, and it's the only thing that self-organizes, self-corrects, and self-sustains.
Hmm.
That's another way of saying the same thing.
Fair enough.
But you're still not comfortable.
I'm just not gonna. You're not going where I'm going at all.
I know.
So
I'm just jumping in with
again, I only have 45 minutes, and we've already been recording for an hour and a half. So I don't have time to say all these things. I've got what I've got.
that's my own question, not
Sure.
yours.
No, that's fair enough. And my answer is I don't know how to answer a question like that because in my mind, these are the laws, and we're going to see them manifest themselves as conventional electromagnetism, and we're going to see them manifest themselves in the laws of gravity as well. We're going to see them everywhere because these are the laws that govern everything. And so I don't separate things the way you do. I just don't see it that way. Sorry. That's not where I was headed.
Okay.
Where I'm headed is I'm just talking about the concept of organization and the fact that when there is a tendency for things to break down. So in other words, the larger circuits, the larger systems would tend to break into smaller systems. That would be called an eddy current. So if you think about it, um, that's where things tend to go, and it becomes and more random over time. And that's basically the law of the increase of entropy, the second law of thermodynamics. But at a fundamental level, at the level of fields, at the level that we're of the infinitesimal, there is no such thing as how do I say that? The field, if you will, is just a function. I mean, it's just this thing that at every point in space it's continuous. There are no uh, there's no point that doesn't have a value. Okay, but what we do have within a field is we have special points of inflection, points where things separate from one place to another. So if you can imagine, I've got two whirlpools side by side, um, and I have an element of matter that's passing through them. It's either going to go to one side or the other. Okay, it has no choice but to do one or the other. Okay, and that point where where they bifurcate, that can be a special point in, if you can think of these whirlpools as similar to our field function. Okay, and so these special points where things are going to go one way or the other, where there's a determination, then there are different ways that we can have these special points mathematically in the field. Those correspond to all the various particles. Okay, so why do particles exist? Particles exist because circuits exist, because circuits separate, because there has to be circuits, there must be these special points, there must be centers to a circuit, there must be points where like if you're halfway between the Earth and the Sun, where the magnetic field is going to either come around the Earth or come around the Sun, but there's a point at which they're going to meet and they're going to go around both. Okay, that special point would be one of these points in space where we could say that's a particle. Okay, a muon or a pion or a boson or whatever. And so in my mind, these things don't have an existence in the sense of tangible existence like a chair. They have an existence in the sense of that the field is telling us something about how things are relating, and that field is going to have special particulate points in our continuum, and those define particles. And when those special points interact with particles, we have quantized events, quantized changes in the way things happen. And that's the concept. We'll talk about more about that when we get to, I believe that's day number 4, the idea of separation. But the point to keep in mind now is all the things that are conserved in quantum mechanics ultimately come from this one law, the idea that circuits separate. It's the law that gives us quantization. It's the law that gives us quantization. Okay, let's move on to the last, which is the idea that rotation shears. And the concept that we want to associate with this is time. Time is the reciprocal of frequency. Frequency tell.
And wait a second. For rotation shears, are you going to show anything?
Yeah, I have definitely,
Okay.
and I'll be talking about this as well. You may remember from 2 laws ago, which I associated with the idea of that motion attracts, which was Ampere's law. This is more associated with Faraday's law, or the Coriolis effect, which you may have heard of. The idea is that we had a time change, which was the motion, and a spatial change, which is the pinch, and that the two were inseparable. You cannot have one without the other because matter is conserved. In this case, we have a time change, which is rotation, and a spatial change, which is shear. Okay, and you cannot have one without the other. They are inseparable in exactly the same way, except here it's because motion is conserved. So in the first case, matter is conserved, we get a law. Here, motion is conserved, we get another law. Okay, and this is the idea behind this. And that I didn't have to say that. Let's think about this now. Let's think about a river. We've got a river, and we've got.
Stop. You said, let's think about this now. Let's think about a river. Instead,
Think about a river.
just
Imagine a river.
or better yet, just have a river up in your PowerPoint.
Yeah. Well, I will.
Look at it.
I will. Okay. So imagine a river. No, a river. Near where the river meets the shore, will all the water in the river travel at the same velocity?
No,
Which water is going to travel faster?
in the center.
Okay, so the water toward the center is going to. Why is it water towards the shore travel slower?
Because it's rubbing up against the bank.
Okay, how about water at the bottom of the river?
Traveling slower.
Okay, for what reason?
Because it's rubbing up against the earth at the bottom.
Right. Okay, so now we have a velocity shear. We have some of the water in the river flowing faster than water right adjacent to it. Do we not?
Yes.
What do you get when you get a velocity shear? Can it just do this forever?
Well, no, because of conservation.
What do you see though? What do you observe at the river's edge?
Curves.
Curves, or maybe even
Waves, but curves.
you can actually see whirlpools, can you not? Little eddy currents?
Yeah.
Eddy currents. So in other words, the velocity, eventually, the velocity where it's moving faster is going to kind of cycle back where it's moving slower, because there exists a frame. If you're kind of traveling with the river and traveling a little slower than the fast water and traveling a little faster than the slow water, you could get into a frame where some of the water was moving forward and some of it was moving backward in your frame. Yes?
Well, because of the shear, what's turning around.
Right,
Yes.
but there always exists, when there's a shear, there always exists a frame in which you can go where you will see that. And so if you see some water moving forward and some moving backwards, you are going to get a little eddy current. Okay, you can't not get it. Does that make sense?
You didn't have to say that.
Okay. How about air? How about weather? Let's talk about what makes the weather move. So we've got currents of air maybe higher up moving faster than a current of air moving slower, moving further down. We have the same thing. We could observe this from a frame in which the faster air is moving a little faster than we are, and the slower air is actually moving backwards from our frame, and we see the same thing. Everybody observing that?
Yes.
Try not to say that. Okay. All right, let's reverse it. So what we know is when there is a shear, there is rotation. Now let's reverse it and say when there's rotation, there is shear. Let's look at a merry-go-round. You're going to ride on the merry-go-round on the inside, and I'm going to ride on the merry-go-round on the outside. We're both moving at the same frequency, okay? But which of us is moving faster? Or is one of us moving faster?
Yours, and your hair is going to go straight out.
Well, if I'm moving, this would be a really fast merry-go-round, or else a really big one. Sure. Okay. So yeah, and how about somebody on the equator versus somebody at the North Pole? Is any one of them moving faster than the other?
The so there I have to think. Oh, because it'll be the same thing. The one on the equator is moving faster.
Yeah. Yeah. He is. Now he's adjusted to his frame, but yeah, he's moving faster. So there's a shear there, is there not? There's a shear between these two riders on the merry-go-round, a velocity shear.
So just wait a second. I have a question.
Sure.
So when a person travels from the equator to Israel, let's say,
Mm-hmm.
part of the if they're traveling by plane,
Uh-huh.
because if you're traveling over land, your body can adjust. When we're traveling by plane, part of the adjustment of the body is the difference in speed and motion.
Possibly, but I'm not sure. That'd be interesting to study if, you know, changing latitudes alone is going to make much difference. I don't know. Because if, for example, if you went from, let's say, we're at 45 degrees north latitude. Suppose we went down to South America, where it's also 45 degrees south latitude. We'd be moving at the same velocity with respect to the Earth, and so even though there'd be no change other than the having gone through the flight. So I don't know. I don't know. That's all speculation on my part because we do adjust. We're not really feeling that motion.
Well, it's a matter of fact that flying by plane does damage to the body. It's a discussion for another
Yep,
time.
absolutely. But anyway, the point I want to make here is that rotation shears, and we certainly see it on the merry-go-round. We could say, all right, well, let's correct it by having you who are closer in move at the same velocity that I'm moving at, but now we're at different frequencies. So now instead of we don't have a velocity shear anymore, but we have a frequency shear. You're moving at a different. You're moving faster on the inner, more times per minute to maintain the same velocity that I'm maintaining on the going outside. So we're going to have a shear there no matter how you look at it. You can't get rid of it. Okay, as long as there is as long as there's rotation, there is a shear. And as long as there's a shear, there's rotation, and the two are inseparable. Again, we have a time change that is inseparably linked with a spatial change, and that's what the equations look like. Okay, and we call it Faraday's law, but we can also, it's exactly conservation of angular momentum. Is Kepler's second law, or the Coriolis effect. The Coriolis effect is related to the fact that there's a different velocity at the equator as there is further north. So when the tides move, they have to, there would tend to be a bunch up. Matter can't bunch up, so it's got to move faster up at the top. When it comes up to stay in the circuit, and that gives us the Coriolis effect, and we get it one in the North Pole, right-handed one, and a left-handed one in the southern hemisphere. Okay, so we can see that, and there's demonstrations, and I can show a movie at this point of the Coriolis effect, so we can get the idea. But that's basically the law. The point I want to make is we think of all these different laws as being separate laws. Kepler's law, Faraday's law, Coriolis law, they're all manifestations of the same thing. Okay, and it's the fact that rotation shears. So what we have now is a basis, and I know I spent more time I should, we have a basis for a natural philosophy which is different than what conventional science teaches. It gives us a basis for understanding all of physics, but on a new foundation, a new framework. It's broken what we know into what we know about groups and what we know about individual things. And by the way, I didn't talk much about expansion, but the transformation of expansion is one that's a group transformation. In other words, you cannot have a dot. An infinitesimal element of matter cannot expand. Only parts of a system can expand relative to the whole system. And likewise, you cannot have a dot that rotates. Only parts of a system can rotate relative to other parts. So those are group transformations. Okay, and I didn't talk about how expansions has to do with the existence, but I will just briefly, just for completion's sake, talk about that. And this is really beautiful, I think. But I talked about the idea that whenever there is a transformation, this is Noether's theorem, whenever there is, when you transform a system and it look,
So wait, stop. You said I talked about the idea that whenever there is, just simply, whenever there is,
gotcha. All right. Whenever there is, and I lose my train. Okay, whenever there is a transformation law, there is a conserved quantity. So this is the question that drove me crazy for a long time. What is conserved when there is expansion? In other words, if you take a system and you zoom in on it and then it looks exactly the same, or you zoom out and it looks exactly the same, what's conserved? Is everybody following? Well, first of all, what kind of a system is that?
Well, can you? It's easier if you give me an example so I
Well, I
can
could
picture
show
it.
you, and if I show you, of course, you'll know. If I show you the picture, you'll know immediately. And I will. I will have a movie of this. You take a system, you zoom in on it, it looks exactly the same. Then you zoom in on it again, there's exactly the same amount of detail as there was.
Oh, the fractal.
Fractal, exactly, fractals. Fractals are quantized because they only become the same when you get to a certain point in the zooming, right? It's like zoom, click, zoom, click, zoom, click. Yes? The
Yes.
clicking is the idea of separation. It's the idea of quantization. But again, what is conserved if I have a system in which that takes place? There's the same amount of
Motion,
no, same amount of
energy.
no, same amount of information. There's the same amount of organization.
Wait, if there's the same amount of information, then there has to be the same amount of energy because the electromagnetic field carries the information.
No, no, forget electromagnetic fields. No, this is not that. This is not a conservation of energy is something else. Conservation of energy is saying that you can't get rid of relationships. This is a different conservation.
All right.
Okay, this is the conservation that says when you expand a system and it remains the same, expand or contract a system, it remains the same. The information content remains the same. That is a measure of information or order, which is neg entropy or entropy. So in other words, in order for a system to be stable, in order for a system to not disintegrate, basically we need a system which is fractal. And so I'm convinced that the ultimate structure of the circuits that govern matter are fractal systems.
So that, in other words, even though my paper is weak, it's more of an essay. The universal fractal flow, you think is true.
Well, again, those aren't quite the words I don't use the words that you use, so it's hard for me to answer that question.
Yes.
But I would say that ultimately stable systems must conserve entropy. If they didn't, they wouldn't be stable. They would disintegrate.
Mm-hmm.
And systems that conserve that look the same through the transformation of expansion, that is, which are fractal, do that.
So
Therefore, I put the two together and say systems that are stable are fractal, and
so
systems that are fractal are stable.
so remember, people coming to the conference want to learn about biophysics. So then we apply this to biophysics. Then we can learn about our digestive system
Hmm.
by studying Birkeland currents, which are millions of kilometers in diameter
Hmm.
because it's fractal.
Right.
So that's why we're going from electric cosmology to electric geology to electric U.
Yep. Okay, I'm trying to get this done here. What I do at this point is go back to page one, and that took a lot longer than I had to do this in 45 minutes. We've been at this for an hour and 45 minutes now. I have to tighten it up. But anyway, we go back to applications on page one. So the applications are to meditate on the fundamental questions. I don't think that we'd spend a lot of time in physics doing this. I may not have all the right answers, and I'm not claiming that I know everything, but I don't think very many people in physics think about these questions in these fundamental ways, and I think that we should. Scripture teaches us that we should, and there's several scriptures that I give to do that. We also, I think, need to spend time challenging each other and ourselves to re-examine basic scientific questions, find new ways to look at them. I think that's always healthy. And then I want to leave you with the idea, how do you answer the basic questions? And that's it.
When you
I'm going to stop the recording now.